Okay, so let's talk about spring mass dashpot system. Okay, this is the system that we are trying to imagine. So on the wall, there is a spring. And attached to it is a block of mass m. And usually for spring, you have the spring constant, so I'll put the k here. K is the spring constant. And then this is connected to some object which we call the dashpot. Dashpot. Yeah, but it basically, it's something like you have something like a piston inside, and there's a hole at the end. Making this hole bigger will make this block easier to go that way. Right? So if the hole is pretty small, then it's going to have more friction. So Dashpot is a system where you can change the friction of a system. Okay, we will just ignore the friction in the floor. So we'll just think as this, if this is a frictionless floor. This is frictionless, and the only friction is provided by the dashpot, and we will talk about the friction coefficient as C. So C is a friction coefficient. Okay, and what we want to do is we want to push the block in one direction and release it, and then what's going to happen? It's going to swing back and forth, right? And eventually, because it has a friction, eventually it's going to stabilize to almost zero. So it's going to come back to the equilibrium. Okay. So that's our system. Okay. So what we have is sum of the forces equal to ma. That's how you solve questions in physics, right? You just think about all the forces acting on the mass m and add them up, and it's equal to ma. But what kind of forces are acting on this? Spring is acting the force, and then the dashpot is also trying to oppose the movement, right? Okay, so these forces are really the force of spring and force of the dashpot equal to ma. That's what we have. Now let's think about these two forces. So first, the force on the spring is there's a law that governs the forces of the spring. What is it called? Yes?
Kx.
Yeah, what's that called though?
Spring constant.
It's called Hooke's law, right? Is it with an E?
Yes. Isn't it negative?
And it's negative. Why is it negative?
Isn't it because it's going in
The opposite of the
direction,
displacement. Right? X is the distance from the equilibrium. Displacement from equilibrium. And if you pull it, then it's going to try to come back to the equilibrium. So the direction of the force is always the opposite of the equilibrium. Okay? So if you say this is positive, when x is positive, the force is going that way, so it's negative. Right? Okay, so this is the one that governs the spring. Okay, what about the dashpot? Well, this one you haven't seen it before, but it basically works like this. the faster you try to move to one direction, the more force will try to go against it. Okay? So think of it this way. If it's not moving at all, then how much force does the dashpot act on this? Zero. It doesn't do anything because there's no friction needed to counter the movement. And the faster you try to move, the faster this block tries to move, it will counter it. So for this one, what you need is it's proportional to the speed. And because it's always trying to act against the direction it's moving, it should be minus of this. So once you figure these out, then you can plug it back in here. You get negative kx minus cv equals to ma. This is, yes,
C is just the Dashpot's coefficient.
Dashpot's
friction, right?
coefficient, so you can say it's the friction coefficient. I actually don't know the correct name for this. Okay, so now what can we do? We can just move everything to the other side. So we can say 0 is equal to ma plus cv plus kx. Okay, is this a differential equation?
Yep.
Why is this a differential equation? Because a is the second derivative of x. V is the first derivative of x. And now if you write it this way, it's a differential equation. So this is the differential equation in case where you don't have any external force. So this is a spring mass Dashpot system. Without external force. There is a vibrations course that you take as an engineer, and in that course you'll be solving this equation many times. The reason is, although we're just talking about spring mass Dashpot system, any kind of vibration is similar to this. So I think the most common thing that people use as a metaphor is if you have some big block on a rubber pad, okay, and if that you push it down, okay, and then the rubber pad acts like some kind of a spring, right? And also there's all kinds of friction acting on this, right? And then it starts to vibrate up and down. That's like this, okay? Now there's also the case where you have the external force. If you have another force, see, if I had an external force, so with external force, it goes like this. There's the F external minus Kx minus Cv equals to Ma, right? And then if you move everything to the other side, then I have the external force equal to mx double prime plus cx prime plus kx. That's the case when you have the external force. So this one is with external force. And oftentimes, this external force will be a periodic function. And the reason for that is, think about a washing machine. Okay? There's something rotating inside, so it vibrates naturally, right? So it vibrates naturally, but you want to reduce its vibration by putting some kind of rubber pad under it. Okay? And you want to think about what kind of effect this rubber pad has to this washing machine. But if you think about it, the rubber pad itself is already spring mass system, just as I explained, right? And the self vibration of the washing machine acts like Fe. So you have some periodic force function present in the system, along with these natural constants in the system. And then you have to solve this differential equation to figure out what's the amplitude of the vibration that you end up with. And that's what you're going to do in the vibrations course. Okay? All right. So these will be something that we will try to study in the Monday more. But let's talk a little bit more about this system. So if you have mx double prime plus cx prime plus kx equal to 0, what kind of solutions does this have? How would you solve a differential equation like this? What do you do? You first think about m r squared plus c r plus k equal to 0. You first think about the characteristic equation, right? Now, what kind of solution do you get out of this characteristic equation?
C.
X is c1 e to the
R1x.
r1t. Now, these are functions of t. Okay, x is a function of t.
Well, how do you know if they're like? How do you get the R's?
You solve this. You get two solutions, and those are the solutions. Okay? You can solve this. It's a quadratic equation. You can solve it using the quadratic formula.
With the letters?
No, I'll be actually giving you the actual number, of course. Yeah. Yes.
Is it never going to be any of the other cases?
Actually, that's the problem. What would happen if you had solutions of the characteristic equation as, say, complex numbers? What are you going to see?
Sine and cosine.
Sine, cosine, right? So if you find a solution in terms of r equals to negative c plus minus square root of c squared minus 4mk over 2m, this is what you're going to see. First, you can show that if this is positive, these two solutions will always be negative. So the two solutions, R1 and R2, will always be negative. So you have something that's decreasing, which kind of makes sense. You don't want your x to be increasing without a bound. That's not that physical, right? So that's the case when this is positive. So this is the case when c squared minus 4mk is positive. But there are other cases. What if c squared minus 4mk is 0? What happens? X is? When this is 0, what should you do? What happens if this is 0?
Negative c over 2.
What's 0?
If c squared minus 4mk, this part is equal to 0, what happens to r?
It's negative c over 2.
What's the square? What's the square root of 0?
It's
The square root of 0 is 0.
I thought it was like undefined or something.
No, it's c1 e to the negative c over 2m plus c2 x e to the negative c over 2m.
Right. In other words, you have, if this is 0, you only have one solution. You don't have two solutions. In that case, you have to find the second solution by multiplying by
X.
t this time.
Oh,
C1 eats a negative, let's just say R1t. And then the second one should be C2 times t times e to the R1t. This is because you only have one solution in this case. What if you have c squared minus 4mk less than 0?
Sine, cosine.
You're going to get sine and cosine. Your solution will look like e to the some at. So actually, it'll be a negative number, and you're going to get one that's cosine wt and another one that's at sine WT. Here I'm assuming that your solution looks like R equals to negative A plus minus WI. I shouldn't really say W, but this is supposed to be omega for angular velocity. So you have these three cases. And those will be separately called underdamped. No, this is overdamped. Overdamped, critically damped, and this will be underdamped. Of course, there's the third case where there's no damping at all. If there's no damping, what happens? It will never stop. It will always vibrate, right? That's the case when A is equal to 0, so it's always a periodic function. There will be no damping. Okay? But if there's a little bit of damping, it still vibrates, although it becomes 0 because of this. And if it's either critically or overdamped case, in that case, it will gradually just go towards the equilibrium without any vibration at all. Yes?
For the equal to zeros equation,
Mm-hmm.
the plus C2, is it C2TE?
C to T
Okay.
times E to the RT.
Right, thank you.
Okay, thank you.